On the morning they poured the final concrete for the spire, workers at the top of the Burj Khalifa were standing higher than any construction crew had ever stood on a man-made structure. The wind at that altitude behaves differently. It does not gust. It pushes steadily, firmly, as if testing whether the building deserves to be there. It did. The Burj Khalifa in Dubai stands at 828 meters. That is taller than the second and third tallest buildings on Earth combined. But the number alone does not tell you what it took to put it there, on a patch of desert ground that engineers at first were not sure could hold it. The story of the world's tallest building is not really about height. It is about what happens underground. Dubai in the early 2000s was a city moving faster than its own plans. Sheikh Mohammed bin Rashid Al Maktoum, ruler of Dubai, had watched neighboring Abu Dhabi sit on oil wealth while Dubai's reserves ran thin. He made a decision that defined his era. Dubai would not sell resources. It would sell itself. Tourism, finance, real estate. The tallest building on Earth would be the advertisement. The commission went to the American architecture firm Skidmore, Owings and Merrill. Adrian Smith led the design. The target height was kept deliberately vague during construction, so competitors could not plan to beat it. That secrecy was not paranoia. It was strategy. Smith's design took its shape from a regional desert flower, the Hymenocallis, a spider lily. 3 lobes radiating from a central core, each stepping back as the building climbs. This was not decoration. The shape was structural logic. Traditional skyscrapers face a problem at extreme heights. Wind does not just push, it creates vortices, spinning columns of air that can lock onto a building's resonant frequency and shake it apart. Engineers call this vortex shedding. The Burj's spiraling, asymmetric form breaks the vortices before they can synchronize. Each setback disrupts the pattern. The building essentially confuses the wind. That solved the upper problem. The lower problem was harder. The ground beneath Dubai is not uniform. The top layer is loose sand and weak sedimentary rock called gypsum. Below that, denser limestone. But gypsum dissolves in water, slowly, over decades, and the water table in this part of the Arabian Gulf is close to the surface. A building of this weight, sitting on dissolving rock, will sink unevenly. That uneven settlement, over time, can crack foundations and tilt structures. The engineers at the structural firm Baker knew this before the first shovel touched the ground. Their solution began 192 meters below street level. The Burj Khalifa sits on 192 reinforced concrete piles, each 1.5 meters in diameter, and driven deep enough to reach the solid, stable limestone underneath the gypsum layer. Together, those piles carry a load of roughly 900,000 tons. The pile cap, the massive raft of concrete connecting them, is 3.7 meters thick, poured in a single continuous operation over 3 consecutive days to avoid cold joints that could crack under pressure. 3 days, non-stop. Concrete trucks arriving every few minutes, around the clock. The concrete itself was engineered specifically for Dubai's conditions. Standard concrete cures through a chemical reaction that generates heat. In temperatures above 40 degrees Celsius, that heat can cause cracking. The mix used for the Burj included fly ash and slag, industrial byproducts that slow the reaction, lower the heat, and produce a denser, more waterproof result. Ice was added to the mixing water to keep temperatures down. Chilled water pipes were embedded in the pores. The building's own weight had to be managed as it rose, because settlement does not wait for completion. As floors were added, sensors embedded in the piles transmitted live data on how the foundation was responding. Engineers adjusted their models in real time. The building was, in a sense, telling them how it felt. And they were listening. Concrete alone could not build this high. The core of the Burj Khalifa uses a high-strength concrete with a compressive strength more than double what most residential towers require. But above the 156th floor, Even that mix would have been too heavy to pump. The structural core transitions to structural steel in the upper sections, two different materials, one continuous spine. Pumping concrete nearly 600 meters vertically was itself an engineering first. Standard concrete pumps cannot generate enough pressure for that height. A custom pumping system was designed, one that maintained consistent pressure across the full vertical rise and prevented the concrete from separating in the line. The system set a world record for vertical concrete pumping, a record held for years after the building's completion. At the 580-meter mark, the construction team faced a constraint no one had fully anticipated. The cranes that built the lower floors could not reach the upper spire. Self-climbing cranes, which grip the building's core and jack themselves upward as floors are added, had to be custom designed for the Burj-specific core geometry. Each jump, raising the crane to its next working level, had to happen during wind-calm windows, because at that altitude, the crane's own structural tolerance could be exceeded in a strong gust. There were days the work stopped entirely. The wind decided the schedule. One such pause stretched nearly a week in 2007. A sustained period of high-altitude gusts grounded crane operations and delayed a critical steel placement. The project managers had built float into the schedule precisely for this. The delay was absorbed, but it was a reminder that height is not a contractor's to control. The cladding, 26,000 individual glass panels covering the exterior, was another problem of geometry. Because the building's profile tapers and rotates as it rises, almost no two panels are exactly the same size. Each was cut to specification, then fitted by crews working from suspended platforms in conditions that would ground most work sites. The total glass surface area covers roughly 17 football pitches. The building was completed in 2010. At the opening ceremony, Sheikh Mohammed watched fireworks launched from the facade. He had announced the building's final height that day, 828 meters, for the first time publicly. Until then, even contractors on site had only known it was tall. He had kept the number secret for 6 years. The Burj Khalifa's completion changed the map of what urban construction firms believed was achievable. Before it, the tallest building in the world had been the Taipei 101 in Taiwan, at 509 meters. The Burj did not edge past that record. It shattered it by more than 300 meters, a gap larger than the Eiffel Tower. Engineers who worked on the project have said in interviews since that the pile foundation was the critical decision. Not the spire, not the glass. The 192 piles driven into the desert floor before a single floor plate was cast. A building is only as tall as its foundation allows. The Burj Khalifa still holds the world height record as of today. Several projects, including the Jeddah Tower in Saudi Arabia, have been designed to surpass it, but none have been completed. The Jeddah Tower, planned to reach 1 kilometer, began construction and then paused, its future uncertain. The Burj remains. What the project demonstrated was not simply that humans can build higher. It demonstrated that the constraints on height are mostly engineering constraints, and engineering constraints can be solved given enough time, enough data, and enough willingness to instrument a building before it is built and listen to what it says. The desert under Dubai did not stop the tower. It became part of the design. Whether anything will surpass the Burj in the coming decades depends less on ambition and more on whether another city in another desert or another delta is willing to spend 6 years listening to its own ground before it starts building upward. The story of this project is still being written. In the settlements measured by sensors, in the wind data collected at altitude, in the engineering papers still being published about what was learned. The building is finished, the knowledge it produced is not.